the extreme value theorem states that a continuous function on a closed interval a comma b always attains a global maximum value. And we're going to rigorously prove this from the basics in this video. It's a great introduction to real analysis ideas and formal mathematical proofs, and it's going to be presented super intuitively. So let's just dive right into it. So what we're going to do is we want to show that there is a c inside the interval ab such that f of c is greater than or equal to f of x for all x inside the interval ab. So f of c is a maximum value. Now we need to understand how are we going to justify the existence of f of c. Now there are two possibilities for what f could do, and we have to think about both of them in our proof, and we have to address them. So here's the proof. The first thing we have to show is that f is actually bounded. Okay, f is bounded. What does that mean? That means that the range of f, so I'm going to write this out as a second step. The range of f, this is f of a comma b, all the values of f, is a bounded subset of the real numbers. Okay, so it doesn't have points that are arbitrarily large or arbitrarily small. It's within some closed interval itself. Okay, so we have to actually show that. But I'm going to do that at the end because the idea for showing that is very similar for this one, and this one is going to be the main focus of the proof, is that assuming it's bounded, this set, this range of f is bounded and non-empty. Okay, it's a bounded and non-empty subset of the real numbers. So therefore, there is an axiom of the real numbers. It's called the completeness axiom, which states that it has a least upper bound. Okay, so there is a smallest number, big M, that is greater than or equal to all the points in this set, all the values in the range of f. Okay, so we can say that this is the completeness axiom. This is the least upper bound property for the real numbers. There exists a big M such that f of x is going to be less than or equal to m for all x inside the interval, and big M is smallest with respect to this property. Okay, so there exists such an M, and M is smallest with respect to this property. Now, this is the least upper bound property in the real numbers, and now the goal of the proof is to show that once we've shown that, okay, this M is there, we then need to show that this M is actually attained by the function. Okay, so we know that f of x is less than or equal to m for all x. So if we know that m is the image of some c, so it's equal to f of c, then we're guaranteed that f of c is the global max. But what we don't know is that there is a value c so that f of c is m. Okay, that's what we need to establish, and that's going to be the goal of the proof. Now, the idea is that you can get as close as you like to m. Okay, so m is the least upper bound. That means it's the smallest number that's greater than or equal to all the f of x's. So it's the least one, so that means we can find x's so that f of x gets as close as we like to m. So let's do that. Okay, so we're trying to hunt for our c so that f of c is m. So let's first find values of f that are really, really close to m. So here's what we're going to do, is we're going to pick, so I'm going to write it here, we're going to pick xn. So I'm going to say pick xn such that, so xn is a point inside the interval ab, I'm being very precise, such that f of xn is going to equal to m minus 1 over n. Okay, so very, very close to m. Okay, so as n gets larger and larger, f of xn is going to approach m. Okay, and I'm going to do a visual schematic of this right now. Here's the visual schematic. So if we think about our graph of our function ab, we know that m is the smallest real number that's at least all the values of the function. Okay, we just don't know it is a value of the function. If you think about the graph, we know that because of our construction of these xn's, we know that there are all these points, okay, these xn's, they are getting closer and closer to this value, this horizontal line of all y values equal to m. Okay, so we can kind of choose points that get closer and closer. Okay, so because we know that f of xn is equal to m minus 1 over n. Now somehow we want to say that because all these values are getting closer and closer to m, there is some point c inside ab that actually hits m. Okay, and here's one possibility. Okay, this is going to be the obvious thing to try, and it gets really close. That's always a good tip in math. Think about the obvious thing. Because we know that f of xn is m minus 1 over n, suppose, okay, so let's assume, this is going to be a false assumption, but it's going to give you an idea. Assume that our xn's converge. Okay, so assume that xn has a limit which is equal to x. Now we don't know that. In fact, in the picture you can see it's really scattered. It's sort of random, and that's a case where, it wouldn't actually converge to an x. But let's assume that xn converges to x. And we're going to use the continuity of our function because this is crucial. Like, for example, what could happen if your function is not continuous is you could have a hole in the graph, you could have something like this, and at the whole it could be something like this. And in this situation, that maximum value m, that hypothetical m, isn't actually a value of the function, but it is greater than or equal to all the values of the function. Okay, it's strictly greater, and it's the smallest number strictly greater than all the values of the function. So we need to avoid these holes, so we need to use the continuity. So let's use the continuity here. Assuming xn converges to x, then we know by continuity, so because f is continuous, we can guarantee that that means that f of xn converges to f of x, right? F of xn converges to f of x, but f of xn, we know f of xn is equal to m minus 1 over n. So therefore, f of xn converges to m, and that means that m is equal to f of x. So we found our c, okay, in this case our x is our c, but we found our value c, so I could even maybe replace it with c. We found our value c so that, you know, f of c is equal to m. Okay, it didn't really matter what we called it, but I'm just going to do it there just to show you. The problem with this argument is, as I said, the xn's don't need to converge to anything. And this is where we're going to invoke the most important theorem in calculus that people never learn. I've done a video on it, but I'll explain intuitively what it is, and I refer you to that video for the detailed proof. But the theorem is the Bolzano-Weierstrass theorem. Okay, the Bolzano-Weierstrass theorem says that although we have a sequence that sort of moves around like this, as long as it's bounded, it always has a convergent subsequence. Okay, so a subsequence means some of the terms converge, an infinite number of the terms converge. It could be not all the terms converge, but some of them do. For example, if I had a sequence that jumped around between 1 and minus 1, it's not true the sequence converges to anything. There is no limit, but every even term or every odd term, that is of course constant and converges to something, either 1 or minus 1. So the Bolzano-Weierstrass theorem says even with a weird sequence, there's always a convergent subsequence that exists, because if the sequence is clustered in some interval, okay, so the theorem states that a bounded sequence of real numbers always has a convergent subsequence. And because we're working on a closed interval AB, which is necessary because our theorem is false otherwise, okay, so our theorem is false if we are working as a continuous function on minus infinity, infinity, you could just take f of x equals x, and there would not be a maximum. So Bolzano-Weierstrass says a bounded sequence has a convergent subsequence. So what we can do is, although our xn doesn't converge, okay, we can find a subsequence that converges. So we can just modify this. We can find a subsequence xni, okay, so here this could be some infinite collection of terms of the sequence that converges to c. And then we don't need to use assumption, we can say that there exists this by the Bolzano-Weierstrass. So the Bolzano-Weierstrass theorem implies that there exists a subsequence xni that converges to c, and then since f is continuous, f of xni converges to f of c is equal to m. And here f of xni, because it's an infinite collection of terms of the sequence, f of xni is converging to m because it's going to be m minus 1 over ni, and the ni's are going to go to infinity. So that's the trick basically. We're invoking Bolzano-Weierstrass to guarantee that there is a global maximum. And for that, I will direct you to that at the end of this video. I'm just going to give a couple of comments. So the first comment, which is important, is why do we know our function is bounded in the first place? We assumed that our function was bounded, and then we said that there is a least upper bound of the image, which we called m, and then we guaranteed that m is the value of the function. But why should m exist in the first place? The idea is very similar, and I want you to actually think about this, think about how you'd modify this proof to deal with that case. And I'll just give you a quick idea, and I want you to think about the rest and drop a comment down below. To show that f is bounded, what we are going to do is that pick xn such that f of xn is equal to n, assuming it's not bounded. Okay, so if it's not bounded, we'd be able to pick an xn so that f of xn equals n, and then run the same argument. Run the same argument to show that the xn's are a sequence, they have a convergent subsequence. I'm going to leave that as an exercise to you to then derive a contradiction and therefore conclude that f had to be bounded. So its image had a bound m, and then our proof runs through. Okay, so that would complete the proof of the extreme value theorem. And one other way of looking at it, which I like for the case of showing that f is bounded, which may be interesting to you, aside from using the same argument, is to think about the extended real numbers minus infinity, infinity. Okay, so you can kind of think that it's true that any non-empty bounded set of real numbers has a least upper bound. in the real numbers, but it's also true that any non-empty set of numbers that are extended numbers, real numbers in general, does have a least upper bound in the extended real numbers. That upper bound could be infinity if the set of real numbers is itself not bounded. Okay, so in that case you could sort of do the same idea. You could then say m is infinity, and you're sort of applying the same principle. You're basically saying that m minus 1 over n approaches m if m is finite, but if m is infinite, then n approaches m. So you can pick the values of the function to approach m. Okay, now that's the proof of the extreme value theorem. So I recommend you check out my video on the Bolzano-Weierstrass theorem. It's going to pop up on the screen here. I'm going to see you in that video, and I want to give you an exercise. Drop a comment down below why the extreme value theorem fails if the function is either discontinuous, I've given you an example of that, or if the interval itself is not a closed interval. Suppose it's an open interval, what's an example of where the theorem fails? And even give me an example where the function itself is not bounded, okay, in either of those cases. One other question, drop a comment down below. What happens if I apply the extreme value theorem to minus f? What is a global maximum of the minus f function? What does that correspond to for the f function? It's pretty interesting. So drop a comment down below and let me know. And if you're really enjoying my content, don't forget to subscribe and like my video, and also check out my Patreon. It really goes a long way to helping me create infinite free accessible math education. I do everything on my own. I love doing it, and I really want to outsource it and deliver education at all levels to everyone, popularize it, and by outsourcing a lot of the work, that would really go a long way by getting support on Patreon for me to do so. So check that out too. So thank you so much, and as I said, check you out I'll catch you in the Bolzano-Weierstrass theorem video over here, or if you like, there's another video on my channel you might enjoy. Both are going to be great. I'm super excited to see you in the next video.